Okay, next we have Mark Irby-Gill coming to us from Red Rocks Community College, transferring to Colorado School of Mines to study geological engineering.
Good morning, everyone. My name is Mark Irby-Gill. This morning I'm presenting rolling down the river. What impact do harder rocks have on a river's foundation as they travel downstream? And I'd like to thank my mentors for their contributions, Vanessa, Gabel, and Gregory Tucker. Next slide, please. All right. The pictures up top compare the contrast and sound of heavy metal and classic rock to the contrast between softness and abrasiveness that can be found in the Laramie Formation and the Coal Creek quartzite pictured on the right. Some call heavy metal more abrasive than the metal vibe of soft rock bands. In this project, we explore the same contrast and the relative hardness of different rock types found in the gravel load of a small river, seen here on the bottom right, and investigate whether their ability to break down or abrade increases the sediment's ability to wear down the stream bed as they travel downstream. Traditionally, the stream-powered bedrock incision law, seen on the bottom left, has been used to model river incision in the bedrock. K, the erodibility coefficient, represents how easily the bedrock on the stream bed will erode, but assumes that the stream is not carrying a sediment load. While this makes modeling landscapes easier, it does not capture the dynamic process of stream evolution. We expect to find that harder rocks will remain larger in size for longer distances downstream, causing them to have a greater impact on the geometry of the river. Improving our ability to predict the evolution of river geometry, which includes metrics such as channel width, slope, and water depth, have many relevant implications for humans, including knowing when and where the land adjacent to river systems will wash away. So how do we quantify lithology and its relationship to sediment supply? Next slide, please. Coal Creek, which drains the eastern side of the Colorado Front Range, provides a useful case study because its catchment lithology includes a mixture of highly resistant quartzite and much weaker sedimentary rocks. We use geologic and topographic maps of the surrounding Coal Creek's the area surrounding Coal Creek's drainage basin to identify the types of rock we should expect to see. Its headwaters are on the left in Golden, Colorado, and it ends at its confluence with Boulder Creek in Erie, Colorado, up towards the upper right. Note the rapid change in elevation known as the mountain front. We also measure the size using a gravelometer pictured on the right and identify the lithology of stream sediment, making sure to capture a representation of the bed sediment every 5 kilometers over a total distance of 57 kilometers. Out of the 8 rock types that supply Coal Creek's watershed, only 3 are non-sedimentary. XQ, which is quartzite, XFH are gneisses, and XG granite are all Precambrian metamorphic and igneous rocks. QAL is composed of alluvium, gravel, and aeolian deposits. After collecting the field data, we consider how best to display it. Next slide, please. These graphs all use the same colors to differentiate the different lithologies, and legend is here in the middle. Graph 1 shows the proportion of each lithology on the y-axis plotted against grain sizes on the x-axis. These are the largest grains plotted, and the largest grains plotted are on the left, and then the smallest are on the right. Graph 2 illustrates the proportion of bed material by lithology on the y-axis and the distance from Coal Creek's confluence with Boulder Creek on the x-axis. Upstream is on the left, and downstream is on the right. Graph 3 shows the median grain size on the y-axis, again plotted against the distance from the confluence with Boulder Creek on the x-axis. And graph 4 illustrates the largest grain size on the y-axis with the distance from the confluence on the x-axis. The blue arrows indicate areas that were inaccessible for data collection, and the orange arrows point to the mountain front, located at 47 kilometers. The red arrow on graph 4 shows the rapid decline in larger grains after the mountain front. What does this mean? Next slide, please. The durable composition of quartzite allows these grains to maintain their size for longer distances compared to the softer sedimentary rocks and the fragile components of igneous and metamorphic rocks. The pictures on the left and right show the relative difference in durability. The ones on the left are the sedimentary rocks, and the ones on the right are metamorphic and igneous rocks. Large sedimentary clasts are rare but do occur. These are likely from local hill slope inputs and do not appear to persist very far downstream. We should consider the lithology of the bedrock that supplies stream sediment because this exerts a control on median grain size. And the picture in the middle shows Coal Creek on the left and its confluence with Boulder Creek on the right. The cloudy appearance of Coal Creek indicates a higher suspended sediment load, indicating that the sediment supply is predominantly finer, less dense sediment. This project has enabled us to develop two hypotheses concerning the potential effects of a quartz-rich bed load being carried across sedimentary bedrock. The first hypothesis is that the harder, more resistant bedrock abates the bedrock below more efficiently, leading to further erosion of the bedrock, demonstrated in the diagram on the left. And hypothesis two, displayed in the diagram on the right, we think that more resistant rock can preserve the bedrock during periods of lower discharge. The river would be strong enough to carry away the finer, less dense sediment within the gravel bed, also called winnowing. This allows the harder rocks to shield the finer sediment below the gravel surface and preserve the subsurface, also known as armoring, which is kind of shown with the thick black line here. And testing these hypotheses will require additional data. And ultimately, the results from the study can be expanded by collecting missing data from the three sites that we did miss on Coal Creek, and also by replicating the study on a similar stream nearby and comparing the results, or by increasing the precision of rock identification in specific units. Because I have a picture here on the bottom right that shows, even though we split it up into igneous, sedimentary, and metamorphic, there are various types of each rock, and each one of those may have variances in their durability. So yes, next slide, please. And here's my acknowledgements, and next slide. Next slide. Next slide, please. No, this didn't show up. Oh, there we go. Okay, awesome. So if anyone has questions, I can answer those.
All right, great. Thank you so much.
Thank you.
So I have a question. So about quartzite. So quartzite is metamorphic, right? So why is that classified differently than the general metamorphic?
Because quartzite in the Coal Creek area is like ridiculously hard and durable. So it actually persisted. Casey, if you can go back to slide 4. Next one. Yeah, perfect. So on this graph, you can see here the quartzite is in the pink, and basically in the
which graph are you?
So any of the graphs, they're all the same color. Okay, so basically in the first one, what you see is that the quartzite is going to be dominating the proportions for any grain size. And in graph 1, in graph 2, what you see is that it persists in the makeup of the bed load all the way downstream, even though if you go to the previous slide, please, Casey. Right here where that yellow arrow is pointing is the Coal Creek quartzite, and the Coal Creek is in red. So this is only the first basically 10 kilometers of the river at the headwaters. And this is the only place where the quartzite occurs, but we find it all the way down to the end, all the way out in Erie. So that means that even though it was supplied at the beginning, it's lasting all the way until the end. And if you go to the next slide, please, Casey. And then on graph number, graph number 3 here, we have the median grain size. You see right there at the top, there's a purple dot that is a sedimentary rock. And what it shows is that even though sedimentary rocks do come into the stream in large size, they immediately break down into finer particles. So they're not really affecting the river as much as the quartzite, which is persisting all the way downstream, even though it was introduced way earlier in the system.
Right, excellent.
Thank you so much.
Thank you. Great presentation, Mark. There is a question in the chat that, for the sake of time, I'm going to let you answer in the chat. Do you think climate change will affect future STEAM evolution? Okay, and then we're going to move on to our next speaker.